It's a bird, it's a plane, it's USB Type-C, it slices, it dices, it juliennes, it leaps buildings in a single bound. Wait, maybe I'm mixing up my analogies here. We're all pretty excited about the amazing things USB Type-C brings to the table. More charging power, more bandwidth, smaller connectors that go, wait for it, either way. Finally, I don't know how many times anyway. But all of those cool capabilities of USB Type-C aren't just going to design themselves into our designs now, are they? As system designers, we've got some work to do on power, signal integrity, and a few other key issues. No, USB Type-C isn't going to give the caped crusader a run for his money or save the world, but the potential advances in USB Type-C technology is going to shake some things up. Hi, I'm Amelia Dalton, host of Chalk Talk. Luckily, we don't have to all design USB Type-C from scratch. My guest today is Matthew Tyler from Semiconductor, and we're going to discuss solutions that will help make USB Type-C implementation a snap across a broad range of applications. And before we get started, don't forget to click that link. There you can find out even more information about USB Type-C solutions from Semiconductor. Hi, Matthew. Thank you so much for joining me today.
Hi, Amelia. How are you?
I'm great. Thank you for asking. Okay, so I know that USB Type-C is here. People are adopting it. We all need to be designing it in, or considering it at least, for our new projects. How much adoption are we seeing now with USB Type-C?
Well, that's a great question. We've been talking USB Type-C for a long time, and now we're seeing a large number of smartphones switching over to the connector. We've seen laptops now in really almost mass scale starting to move. Most of the new developments have all got Type-C on board. I even found we've got inquiries coming in from set-top box, from cable modems, from peripherals, power accessories. There is a lot of design activity happening now in the market. Lots of excitement around it because, really this brings some new capabilities, or if nothing else, it kind of takes away that frustration of why isn't my USB connector going in the hole because it's not facing the right direction.
Right. And I personally really hate that. Okay. So one of the things that really distinguishes USB Type-C is the power delivery spec. Now, it seems that opens up whole new possibilities in charging and powering our devices.
You're right. And maybe I don't want to get on a soapbox, but if we think about it, we do need to separate USB PD and USB Type-C.
Okay.
They are independent things. Now, the connector brings, I think, additional value and capability, but if we say Type-C at the end of the day, it's still just a connector.
Sure.
So what USB Type-C paired with PD brings us is, well, just more power. Now, how does that work? If you look at the classical USB micro B connector, you can push about an amp, 1.8 amps through the connector technically is where it's limited. Some people push it a little farther. Maybe the cable life and connector life goes down, but That's really where you're constrained. Because of the symmetry of the cable and an additional pair of power interconnect inside the connector, now we can get 3 amps out of the cable, and it's more reliable.
Nice.
So that's really the exciting piece. When you look at the whole spectrum of parts that are there, as you can see, we've got little tiny batteries and wearables, and most everybody's got a pair of Bluetooth earbuds now that are, the battery's almost the size of the connector itself.
Yeah.
All the way up to, with the ability to mix the data and the high power, now we can actually replace your big clunky docking station for your laptop, or now we've got people talking about, well, what about gaming systems, or what about TVs that only have a USB Type-C connector, all the way up to 100 watts. And even though we haven't seen really a lot of design content coming into the consumer market space at 100 watts, we already have people trying to say, well, how can we push a little farther? Because boy, if I could just get 150, now I could do something cool with it.
Right. Okay, so why we're here today, what does Semiconductor bring to the table with USB Type-C? You guys have a pretty robust set of solutions for us, right?
All right, so After the integration of Fairchild Semiconductor, what we found is that ON had a lot of power solutions and a lot of protection solutions. Fairchild brought the controllers and a lot of the interface solutions that was missing from the ON Semiconductor portfolio. Now, the new ON Semiconductor portfolio is really fantastic. And if you look at physical footprint, if you look at power consumption, we think that we're class leading. And because we have so many different building blocks, you can really optimize the solution to just exactly what you need for your application.
Nice.
So, I mean, if we take a closer look, all the peripheral content that sits behind the USB Type-C connector, you've got the power path, which includes switches and high voltage protection. Something people don't always think about is that a typical use case would be, I'm going to plug my phone into a little commodity cigarette lighter charge adapters for your car.
Right.
Well, because let's just say the quality of those devices may or may not be as high as some of the products you're accustomed to working with.
True.
One of the now normal use cases is if that device fails and passes the car battery voltage straight through your cable, what happens, right? So you've got to protect all the electronics and the more sensitive content from that high voltage. You've also got a lot of power conversion that has to happen. While the USB connector standardized around 5 volts, everything that's connected to it doesn't necessarily run off of 5 volts. So we have lots of options and flexibility around power conversion. Also, the communication protocols or the communication port, the CC port, also what gets connected is the port controller. That's a single wire communication interface that can be quite sensitive, so it has to have voltage protection, it has to have ESD protection.
Right.
We've got a family of port control ICs that I think are really the anchor solutions for this product space. And then we'll talk a whole lot more about super speed and redrivers and ESD protection a little bit later on.
Okay, so I can imagine there are so many scenarios where we use USB and USB Type-C that it's made that ecosystem even more complicated. So can you walk me through some of the typical application scenarios?
Yeah, so while there's a lot of different ways that you can integrate power and data connectivity with USB Type-C and USB PD, there are a few big applications, as I'm sure you know. We've got smartphones, we've got computing, we've got stuff that is really going to be the volume driver in the market, and then all the components that have to connect with that.
Sure.
So if we take a closer look at tablets and smartphones, most of the processing intelligence is really handled by the application processor. And then what we're seeing is as the interface standards and things are stabilizing, there's a lot of room for tailoring the peripheral content. So of course the port control IC is really central to that. Again, you've got a wide range of power management that could include battery charging, battery discharge. A lot of these manufacturers are also looking to differentiate with how they charge their battery.
Right.
What I find really interesting here is if you rewind 2 years ago, a lot of discussion was around quick charge, fast charge.
Sure.
Pick your protocol.
Yeah.
You go back more recently this year after some high profile challenges with lithium ion battery safety, now a lot of intelligent charging. Which is great. It's still a lot of content, but what we're finding is redundancies in protection structures, a lot of intelligent monitoring and things that go on with the battery in terms of voltage and current. So that's getting built into power solutions that I think are really essential, especially with devices that people put in their pockets.
Right.
So,
or on airplanes.
Or on airplanes or in headphones. Or we've all seen the scary news stories. But the good thing is that there are solutions out there that make these very, very robust. But a key piece of that, of course, is being able to communicate across the connector and optimize how much power we're delivering to the battery, how much power is available, what can it consume and tolerate. All that's handled by the port control IC. And then depending on the integration in smartphones, of course, most of these are running into super speed requirements. What we're also finding is that for peripheral interfaces like CarPlay or Android Auto, these all have to have at least a 5 gigahertz connection into the host processor in that device. So super speed is here to stay too.
Okay, so let's talk about all of the things we're doing with USB Type-C, but let's talk about some engineering realities here. What are you seeing in the audio solution space?
Well, the smartphone and the tablet has really changed how we consume media. That's a pretty well understood transition in the market, but audio has been really impacted by all this too. So we see the convergence of industrial design and engineering requirements. And as many people know, recently we're seeing our beloved 3.5 millimeter headphone jack disappear from many of our smartphones or smart devices. So what we're finding then is very creative use of the information and the data that's transacting on the USB port. Well, in many cases, we're seeing multiplexing of high fidelity analog audio onto traditionally digital pins. Many times what a particular manufacturer will do is they'll sell an adapter for their phone that can handshake across the USB Type-C port and let it know that those D plus and D minus pins in the USB connector are now going to become audio pins that we can feed information across.
Gotcha.
Or some of the unused pins in the connector. Or we're even seeing that there's just USB digital audio encoded moving across the port as you would probably expect it to be, and then it has to be decoded into analog somewhere downstream. So
sure.
There's lots of different proprietary solutions. The good thing is that ON has solutions already available and ready to sample for many of those.
Okay, so this may be a loaded question, but what about computers, Matthew?
Well, computers. We do see a lot of changes happening with computer interfaces. Certainly, the USB Type-C connector has really taken hold in laptops and I would say intelligent tablet computing devices, not traditional mobile tablets. And the reason for that is that you can push power both directions. This is one of the first use cases for dual role ports. So, it was a bit of a shock to see a laptop show up on the market that had one USB port.
Right.
Everyone's like, well, now what? Wait a minute. How's that going to work? So in the end, you've got the same port. It charges, it discharges. You can plug a monitor in. You can move data. And depending on the design preferences of the end manufacturer, seeing 1, 2, 3, sometimes 4 USB Type-C ports, I think we're going to continue to see some creativity applied there. Some platforms that are going to favor that very lean, very sleek industrial design will be the leaner side of the spectrum.
Sure.
But the real story here is scalability. You've got to be able to scale, and each of these ports have got to be able to deliver quite a bit of power.
Sure.
So you've got high voltage requirements. Sometimes they're multiplexing in classical 19-volt barrel connector. So you've got additional input paths. So we're quickly building out a portfolio of products that will support the entire computing space.
Excellent. Now, it seems like if I'm just in the business of making power supplies and adapters, that USB Type-C would play well for me.
It does. And the reason for that is that now that you've got one connector, one interface protocol within software adjustments or firmware adjustments, now you can adjust or change exactly how much power you're delivering. You can have one fixed schematic, whether it's a travel adapter or whether it's a power brick or a wall receptacle.
Yeah.
A particular manufacturer can have one fundamental schematic. They can scale a few power devices, some FETs and some diodes and things, maybe the power transformer, and then they can port that solution to multiple devices with very, very small amounts of fine-tuning or, without a lot of additional optimization, they can end up really migrating the same BOM. It's faster and more efficient from an engineering perspective, but we're also seeing a little bit of uncertainty in this space where these manufacturers are like, well, okay, do I focus on a 15-watt solution that's going to service most everything? Do I push to 45? And then how big does it get?
Right.
We're seeing gallium arsenide devices, high switching speeds. And, again, there's always the pressure of the industrial design trying to squeeze down the footprint because no one really likes how these things look stuck in the wall.
Right. All right, Matthew, let's dive a little deeper into this super speed business.
Right. Yeah. Super speed, like I said, it's really here to stay. We look at farther forward, we see the 5G rollout where we've got 10 gigahertz wireless link to our phones. Whatever hooks in or connects into that is going to have to be able to sustain those data rates.
Right.
And already in our cars, in our docking stations, we want high resolution audio and video. So this is going to keep pushing it. So, when we look now, it's not just a simple ecosystem of my PC plugs into these three things and my smartphone interfaces with these three things.
Sure.
It really is becoming a little bit more of kind of a convoluted mesh of stuff, especially with dual role ports. And am I going to be charging some device off of my smartphone because my battery in my phone's got 85% and well, I still want to power up my tablet that's at 3%.
Right.
All that's possible to do now, but it does challenge the engineering solution side of things.
Sure. Okay, so redrivers. Let's get into that. What are we talking about here?
Right. It's funny because a lot of people say, well, why do I care about redrivers? I'll just, I have the signal, I put on a cable, and if I'm worried about it, I'll just draw my PCB layout really carefully.
Right.
And it's going to be all right. But to be certified to USB 3.1, both Gen 1 and Gen 2, there are very specific requirements on jitter, the opening of the eye diagram, and just making sure that, again, every device that plugs into a USB port is able to communicate effectively based on what it was certified to.
Right.
This is an ongoing challenge, and as we look in a little bit more detail, we can see that depending on the length of the connection, how big is the device, how good was the connector, how much degradation did you have over the lifespan of the device. What a redriver really brings to the party is that it can re-equalize and it can open back up that eye diagram. It can help, I would say, more marginal products. Maybe you're really close at 5 gigahertz. If you want to move to a 10 gigahertz design, maybe you don't have to redesign the whole system. You can just add a redriver in and really see some substantial improvements in terms of signal integrity and interface quality.
Okay, so what kind of losses are we facing at these multi-gigabit speeds?
That's a great question. When you look at traditional twisted pair or high quality interconnect, the losses aren't terrible. You push out to 10 gigahertz, some systems can handle 4 to 8 dB of loss.
Yeah.
But it really becomes a function of length. You got impact from cable diameter. You don't always know whose cable is going to be plugged in.
Sure.
So if you go in and certify a device, again, maybe how you certified it isn't exactly how the end user is going to use it.
Right.
And I think again with USB ports, we're going to find that there's some old cable that you dug out of the bottom of a drawer, kind of dusty, and it's got a nice kink in it somewhere.
Yeah.
And you're hoping that, when you go to do your presentation at work, you're going to be able to plug in and that's going to be okay.
Right.
You've always got to have a little bit of margin in designs. What I found interesting when we looked at loss data, though, is that typical PCB losses are substantially higher than cable losses. Everybody knows the connector is going to drop a couple of dB. Everybody knows you lose some of the cable, but really one of the worst things on the system is your PCB.
Interesting.
And it's always funny when you look at large PC platform reference designs from those large microcontroller vendors, you'll always see that the USB super speed port is sitting right next to the main processor, less than a centimeter away.
Right.
And that's because the losses are so terrible, they can't put the connector on the edge of the board. And they don't want to tell you that you have to put redriving and equalization and all these more exotic interface technologies in to make the thing work.
Right.
They want you to think it's simple and inexpensive. So in the end of the day, from an engineering perspective, you're going to have to do some data management or some high-speed signal management when it comes to 5 and 10 gigahertz.
Sure. So how does Semiconductor stack up against the other options on redrivers?
Well, most of the products on the market today were optimized around the 5 gigahertz speed range.
Oh, sure, yeah.
So when we take a look at, what happens when I take those 5 gig products and try to push them all the way to 10, well, as you can see here, it doesn't always work so well.
No.
And so,
especially that last one. No,
right.
Awful.
So some opening to the eye diagram is better than none.
Yeah.
And so we're really pretty happy with, we believe that when you look at the whole connectivity path for 10 gigahertz, we have the most comprehensive set of products that are certifiable and are effective and low power at 5 and 10 gig.
Nice. Okay, so we're dealing with smart cables too in these applications, right?
Right. So that's something else that really we're used to, again, reaching into the bottom of that dusty drawer and pulling a USB cable out and plugging it in.
Yeah.
But with super speed, that doesn't really work anymore. And so the cable has to be able to interface and communicate with the host controller and the device to say, hey, I'm a 5 gig cable, I'm a 10 gig cable. You can use me at certain speeds or else the system is going to basically just fall out of connectivity or it's going to default back to your glacial 480 megabit per second USB 2 standard.
Oh, no.
But also we see the need for redrivers in the cables. This could be at either end of the connector. It could be in the middle of the cable. There's a lot of flexibility, but again, depending on the length that you're looking for, we did a demo at CES and a few other places where we took a super speed docking station, just a hard drive, and we plugged it into a device.
Nice.
And it worked. It worked fine. We put a cable that was just a little bit longer into the device. Nothing would register. Nothing would hook up and run.
Oh.
So again, nobody wants that. People want seamless connectivity with USB. So the system has to function. This is, again, a necessary evil that I think we're going to see really in one of those big areas of adoption is there's a lot of USB cables out there. And as we see them needing super speed, they're going to have a lot of redrivers and controllers inside.
All right, let's talk about another topic around these lines, switches.
Switches, yes. So again, much like a connector, you've got some necessary things that have to happen. The symmetry of the USB-C connector mandates then that once you plug it in, it could be on this side of the connector or that side of the connector.
Right.
So you've got to have a 2-to-1 mux in there somehow that handles multiplexing those lines into the USB 3.1 host controller. So, for example, we got the FUSB 340. This is one of the first devices on the market that was certified to 10 gigahertz. It's fully compliant. But the key thing here is insertion losses, crosstalk, isolation.
Right.
And again, everybody cares about power consumption and footprint.
Absolutely.
So all this is new hardware that's showing up around the connector that didn't used to be there. So with switches, we've got to make sure the signal gets through, and it's kind of the principle of if you don't break it, you don't have to fix it.
Right. Okay, so how do your switches compare with, I don't know, other options out there?
Well, as you can see from our data table, we do feel that our solutions here for USB superspeed switching are world-class. And it's not just one spec or another, but if you look at the total envelope, we've got the widest supply range, we have the highest bandwidth, the lowest insertion loss, or very, very close to it. Mm-hmm. But looking again at differential isolation and crosstalk and power consumption, this is a world-class solution.
Okay, and you guys have solutions for connector protection as well, right?
Correct. So the other piece of this is that the USB connector is exposed to a very treacherous world. One of the worst things that can happen is you,
right?
And that's you touching it.
Yep.
And so when you look at just protecting for ESD, this has always been a challenge in the market where I have really nasty things, big surges and high voltages being imposed on the very sensitive high-speed pins inside the connector. And even worse, when you look at a superspeed connector and the frequency bandwidth of what's transacting or moving across that connector is really similar in terms of the high frequency content that you have in an ESD pulse, right? Mm-hmm. So you see that arc, it zaps onto the connector. Now you're sending gigahertz bandwidth content in at very high energy, so the system has to be able to differentiate from that.
Absolutely.
So very critical things there, of course. At some voltage, it has to turn active and it has to dump all the signal content.
Yeah.
And it has to reject everything else that's transacting or moving on that bus.
Right.
And so to do that, it's got to have really, really low capacitance. It's got to have a small physical footprint. It can't be inductive. Mm-hmm. So again, when you benchmark these characteristics, the on-semiconductor ESD solutions really are world-class.
And what's the competitive situation look like with these?
That's another good question. So, we talked about really how do you differentiate between signal and a fault that's happening on the bus. And the key thing here is the trigger voltage. So if you take a look at this chart, I know this is maybe a little bit crazy or hard to read, but if you look down really, really, really close to the x-axis, there's a voltage that triggers or turns on the ESD protection structure. And then its goal is to dissipate all the current or all the energy that's on that pin very aggressively.
Yeah.
So having a lower trigger voltage is really critical here. And as you can see at this particular batch of competitors, the on-semiconductor solution has a significantly lower trigger voltage.
For sure, yeah.
And even more important than that, as you start to push energy through that device, whether it's 2 kV, 4 kV, 8 kV pulse, the voltage that the system maintains under all that current or power dissipation is also essential, because if any of these rise above the design limitations of the interface devices downstream from the connector, you're going to cause damage.
Sure.
And so as you look at these other devices in the same stress, the same set of conditions, you see significantly higher trigger voltages and you see significantly higher holding voltages under those high current discharge conditions. So it's pretty rare that you can get both a product that has the lowest capacitive loading and the best trigger and holding voltage performance.
Right.
So the on-semiconductor products really bring that to the market with some very innovative design.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Matthew.
Well, thank you for letting us share all of the exciting information and product knowledge we have around USB Type-C.
And before we go, you didn't forget to click that link, did you? There you can find out more information about USB Type-C solutions from onsemi. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, check out the Chalk Talk section of eejournal.com or head on over to YouTube, keyword EEJournal.